Okay. Distinguished guests, ladies and gentlemen, good afternoon and welcome to this session addressing our global challenges through research and innovation. My name is Janne Laine. I'm the Dean of the School of Chemical Technology here at Aalto-Yliopisto. We have two closely connected parts in this session. First, we will have case bioeconomy, and then after the coffee break, we will have case sustainable technologies. In bioeconomy, the target is to utilize different sources of biomass to make novel materials, chemicals, and energy. It requires very many different things. You have to understand recycling of materials, sustainable solutions, utilization of side streams, understanding about carbon footprint, and very many complex matters. In this afternoon, we are going to discuss about those complex matter during this session. I'm pleased to introduce our speakers today. Professor Magnus Berggren, please.
Thank you.
He's a professor and director of the Laboratory of Organic Electronics in Linköping University, Sweden. He's also laureate of the Marcus Wallenberg Prize 2014. So you are very welcome. Please.
Thank you. Thank you.
Then the next one is Dr. Ed de Jong. He's the Vice President of Development Avantium Chemicals. Very nice to have you here today, Ed. And then last but not least, Academy Professor Olli Ikkala from Aalto-Yliopisto. So Olli, please. Today we try to do this session in a way that we first will have presentations by each of the speakers and panelists. Like 15 minutes I have given them time. I have also these 2 minutes signed. They are very talkative, so I think that I need to maybe use that. Anyhow, we will have time for those presentations, and then after the presentations of each of the panelists, we will have also panel discussion plus of course comments and questions from the audience. So the first speaker will be Professor Magnus Berggren. Please, Magnus.
So, thank you very much, Mr. Chairman, and I also would like to take the opportunity to thank the university here and the DREAM team that has put this symposium together. I have enjoyed the start of the day very much, and it seems like it's a great opportunity to also do that the rest of the day. And I hope I can contribute with some ideas on the topic about biotechnology for a sustainable society and what we could do with that. So, my title is about browsing the real world using printed electronics and organic bioelectronics, and the idea is to use this technology for future healthcare and at the same time trying to derive a technology that is sustainable in terms of recycling and the materials that are used to compose the technology. So we have all enjoyed this revolution. I had a great opportunity as a young postdoc to work in the lab where the transistor was invented. I was so inspired, I was completely blown away when I understood that this tiny, almost mechanical device is used in all electronic devices that are produced today, and this is the next generation of tabs that will come onto the market. They will be semi-flexible, and they will be distributed within the next couple of years or so. And it's amazing to see this revolution. It almost adopts many of the features eventually of paper, something that is flexible, that you can fold and maybe bend and roll up and so on. The drawback with this technology is not, besides this e-evolution, it's this. We have e-waste. The electronics that are produced today are primarily made based on inorganic materials, metals, crystalline semiconductors and so on, and they are utterly hard to recycle. So what if we could base this beautiful electronic technology on something like this? If we could actually make electronics, large surfaces, flexible electronics based on this wonderful factory. And particularly in this part of the world, you enjoy the forest very much. I see this as a huge asset from a romantic point of view. I enjoy going to the forest, I enjoy being there, collecting mushrooms and all that, but also it's a huge factory. It's in fact the largest factory on Earth that we are tapping out from. When the plants are put into the soil or when they start to grow, they consume carbon dioxide and spit out oxygen. We can make all kinds of products, fiber-based products based on this. And when we are done with the fibers after many times of recycling, we can simply burn it without any problems with the conscience. And in this burning process, we will spit out carbon dioxide again. And this, in a sense, represents the largest closed carbon cycle on Earth. So, thinking about the volume that is produced with this, if you take the 10-year production of paper and if you assume this is office paper only, that will be enough. The 10-year production will be enough to make a wrap package around the moon. Just think about how much volume that is. And this is in fact a closed carbon technology on Earth. So this has a great potential to become a carbon neutral technology for all kinds of products. But the question is, can we replace electronics with something coming from the forest industry, and that is organic? The vision was there some 15 years ago. I started to look together with my colleagues at the evolution of paper manufacturing. This technology went from a batch-based process into reel-to-reel manufacturing process. You have printing technologies and also paper manufacturing sites that produce paper up to speeds of 150 kilometers per hour. Electronics industry some 15 years ago looked very much like this. We had factories around in Linköping, the city where I'm working. We wanted to take it into this technology. There has been a fantastic work all around the world today, looking at organic materials and trying to make them printable. There has been fantastic work performed, for instance, by Ulikala and also by Åbo Academy and VTT. There has been major achievements done during the last 15 years. So, what can we do with this technology? Can we take it into new kind of bioelectronics? Can we take it into new kind of electroactive or intelligent functions that we can actually print or include into paper? We have to start somewhere. And during the last couple of years, we have looked into take cellulose, nanocellulose or microcellulose, combine it with electroconducting materials like P.PSS, DMSO, which is actually a byproduct from the forest industry, and also glycerol as a plasticizers. So all this together forms this kind of big macroscopic objects where we can actually achieve a very high conductivity between 1 and 2 kilosiemens per centimeter. Okay, that's a number saying that it's a pretty highly conducting material. And we can therefore go to make heaters. We have recently achieved the largest capacitor or charge storage device ever made of organic materials. We can do coils, and we can also make transistors, where we now today have the world record in the transconductance values. Of course, what I'm trying to say here is you can, inside cellulose, establish conductivity, electrical conductivity of values that are of interest for many kind of charge storage or energy storage applications. Okay, let's move into electronics. We have done displays, transistors, antennas, sensors, basically all kind of classical electronic devices. We have developed printing techniques so we can print these devices and form integrated systems onto ordinary paper. Our first achievement was done in 2005. We published it 2 years later, and that was to make a paper label including push buttons, batteries, displays, and some logics. Then we moved towards using this technology into biosensor platform. The idea was to have a single piece of paper label with sensors in order to record chemical or biological or physical parameters of different kinds. Initially, we combined it with ordinary electronics. Today, these labels look like this, and we can manufacture those on the levels of million labels in our machines. There is a silicon chip embedded somewhere. We have electronics, batteries. This is the sensor head, a display, and so on. And we can basically make this into a diagnostic tool. So we can, for instance, make glucose tests with this, and basically any kind of receptors can be included in this sensor head, and this replace the big boxes that are typically stored at the clinical chemical departments within the hospitals that do many of the routine analysis. So please keep that in mind. So another area, I will switch gear for a while. Another area I've been working with during the last 10 years is to connect biological signaling and electronic signaling. We know that the electronics are extremely fast. They are run entirely on electronic charges, and they produce many of the signaling entities of computers today. Whereas in the biological world, all the signaling entities are chemicals. They are neurotransmitters, cations, peptides, proteins, DNA, and so on. Can we make a technology to bridge in between these two worlds? So our target has been to derive a chemical transistor technology, translating electronic signals into neurotransmitters and vice versa. So the idea is to make some kind of interconnects between biology and electronics, and the idea is to go for prosthesis technology and also in vivo medication and pharmaceutical technology. So basically, there is a field today that is named electroceuticals, basically to make electronic pharmaceuticals for future healthcare. So what we try to mimic is the transmembrane signaling. This is the extracellular part of the cell. This is the intracellular part. You have transmembrane proteins. You have a neurotransmitters coming here, and then they open up and you shuffle cations back and forth. This is the signaling every day, every time when we are thinking. All processes in our body are regulated by these transmembrane proteins. They, in a sense, are a chemical transistor. So you put a neurotransmitter, and then you can pass millions of cations through these proteins. And of course, this is the synapse. You heard discussions about this. This is how they work. They have an action potential coming down, and you get this vesicle to burst, fire out the neurotransmitters, and then you have the receiving post-synaptic terminal down here receiving. So this is, in a sense, a transistor amplification. So we have materials which can convert electronic signals into ionic ones. So this is an ionic conducting system, this is an electronic conducting, and you can use this as a translator from the biological world to the electronic or vice versa. So we are trying to mimic these transmembrane proteins by chemical transistors. And I will be a little bit more on the scientific heavy side right now. So the devices we are manufacturing includes an emitter collector, just as ordinary electronic transistors. We have a base. Instead of running electronic charge carriers through the device, we are running ions. So we can accumulate, in this case, positively charged carriers, ions in the base, and by accumulating more ions in there, we can all of a sudden open up a passage so ions can run through. This is very much resembling the functionality of a transmembrane protein in our synapse. And of course, if we take away the positively charged ions, we can deplete the neutral region, and then we cut off the transport of ions. So if these ions are neurotransmitters, if this is cations, this exactly resemble the action potential and then the exocytosis part within our neurons. So this is how the device looks like. We have taken this device, we have studied. This is the base current of ions. This is the collector current going through. And the active mode, the cutoff mode. And then we can do all kinds of tests of this. For instance, we can take this transistor, these chemical transistors, put it in contact with neurons. We use the action potential, open up the passage for a neurotransmitter. The neurotransmitter is exposed to these neurons, and all of a sudden we can record signaling inside these cells. So this is the first test of using a chemical transistor mimicking synaptic signaling to actually regulate signaling. So this was done quite some time ago in our lab. We have taken this technology in order to make, for instance, chemical pacemakers. So we have a device that looks like this. We are sending in an electronic signal, and via electrochemistry, we establish a potential gradient so that the charged neurotransmitter can be transported and then be released. This tip of the device we put in the closest proximity to the organ that we want to regulate, or the neuronal system. And one example of such a system is given here. We are trying to replace the electronic sort of spinal cord pacemakers that are used today to suppress or combat pathological pain. This technology, what we have done basically is to make such an ion pump with 4 different outlets. And the idea is to dispense neurotransmitters at the space or the location of the L3 to L6 dorsal root ganglion in our spinal cord in order to dispense neurotransmitters to combat the neuropathical or phantom pain that some patients are experiencing. So this is the withdrawal threshold, and this is the test analysis we did by just pumping protons or other cations, and this is when we pump neurotransmitters. So we were happy to, in 2009, to report the first in vivo experiment using such a chemical pacemaker. So this, in a sense, this device, we go from an electric signal, convert it into dispensing of neurotransmitters in order to suppress chronic pain in animal models. So we have electronics on paper. We know that we also can make electronics inside our body. And we need a communication technology. How are you supposed to run signals in your body? And together with Ericsson, we started to look into a technology where we have labels in our ambience, we have maybe electronic skin patches, and we have devices in our body. Could we utilize our technology in a future healthcare system where basically you carry along the hospital with you? So you don't have to go to do diagnostics nor dispensing of pharmaceuticals in the future. Of course, this is like a sci-fi vision of a future healthcare. And we discussed this very much with Ericsson, and they started to think, how are we supposed to communicate in our body between devices? So they developed an intra-body network technology where we use capacitively coupling between devices, and they are utilizing our body fluids as the network. This technology has been explored by many other companies, but Ericsson was the first one that actually made this into a stable technology where we now have simple labels, and they are using the smartphone as the capacitive receiver of signals. So where we want to take this technology, our printed electronics and also our bioelectronics, into something that looks like this. So we have our printed labels that we can distribute in our ambience. Hopefully this will be all environmentally friendly, so they can be recycled as ordinary paper. We have skin patches that we are starting to put onto the skin and record a different kind of biochemical parameters on our skin. We are also starting to put devices in our body. So we foresee a future where every item in our ambience, I'm not talking about billion things, I'm talking about 1,000 billion things in our environment, packages, surfaces, everything includes a label. Let's say also a milk package will include this kind of technology. As soon as we touch something, we actually browse the real world. We start to browse our ambience by just touching things. And it turns out that one of the best perceptive haptic equipment we have is our hand. So don't think about putting up your phone, record a QR code. Whenever you touch something, the information will be transported and transferred into your cell phone. And of course, we can think about skin patches also transmitting this information. We can think about devices in our body. We can think about having our smartphone in close proximity to our skin. And this will form a giant network where your body becomes the network. And of course, selected information will be transported also for service providers through the cloud, possibly. And of course, there is a lot of challenges related to safety, security, and integrity, and we are all aware about that, but this is one opportunity for the future where everything around us will starting to include printed intelligence, and where we start to put devices inside our body in a much greater extent. And the idea with this is to establish a situation where the car industry already has done this journey. The car in the 70s looked something like this. This is an Audi. This is an Audi today. They run pretty much the same speed. They are maybe twice as efficient. The main difference is the electronic systems, hundreds of sensors, hundreds of actuators are regulating, auto-regulating the car today. And they are addressing connectivity, safety system, emergency call, diagnostics, remote service, and all that. Why not do the same with humans? We can address exactly the same questions and opportunities with this. And the idea, the main difference between the Audi in the 70s and 2014 is that these are typically not parked along the road any longer. Maybe we can do the same here. So the objective of our research effort is very much to end up with the technology that you can bring the hospital along with you. All right, thank you.
Thank you, Professor Berggren. We will take questions later. Then next speaker will be Ed de Jong. So, please.
Good afternoon. Thank you very much for the kind invitation. It's a pleasure to tell a little bit general more about bio-based economy and also a little bit about my company Avantium. I gave a talk, a critical view of the forest biorefinery to serve the chemical industry. Now, some of you might not know our company, so I will just give you a little bit of background. We are a real SME. We are now around 145 people. We are also, over time, become completely venture capital owned, and that means that our shareholders really wanted to have higher added value in the future, and therefore we started in 2005 our own development program to really look at ways to convert biomass into building blocks for chemicals and or fuels. And what we basically found out that also comparing to our knowledge, conversion of carbohydrates, the most abundant compound on Earth, was very good starting point into furanic molecules, and I will tell you a little bit more about that. What I also will be discussed later during the talk is that to bring really a new kind of chemical to the market, it is very important to have partnerships, both with industry as well as with academia. And I will give some examples why we are very happy, for example, with the partnerships we have with Coca-Cola and Danone. So what will I do today? I will give you a little bit an overview of what kind of value-added products all can be made from biorefineries. And at this moment in time, I will put an emphasis on bulk chemicals. Why is that? Certainly not because you can't make money with specialty chemicals and fine chemicals, but the reason is really that if you want to go to a circular economy and if you want to really mitigate CO2, then we really have to look at bulk applications, and that can be in fuels areas, but certainly also in chemicals area. The next thing I want to touch very briefly is what is the preferred chemical? Is that a drop-in? And you have to think about ethylene compared to bioethylene, or should the molecule be with novel functionality? And both have pros and cons, and I will briefly touch on that. I'll give you some examples of where we are in Europe is that, and wrap up with some conclusions if I'm still within 15 minutes. Good. If we look at the pulp and paper production, it is, in my perspective, a very good starting point to combine pulp and paper production with also the production of fine chemicals. Why is that the case? I mean, I just put a couple of attention points here on the screen. So it certainly can improve the economics. It can make the scaling up easier because the plant already is commercial and a new addition at a smaller scale. You can certainly, you have CO2 storage sinks, and what is an important aspect to keep in mind is that you can use existing assets of of a pulp plant, and especially regarding steam and electricity, but also wastewater, biomass logistics, what is a very important point, and other things like fire brigade, etc. And don't underestimate the importance of those kind of things, because really, if you want to go into bio-based chemicals or biofuels, then the capex demand, so the capital expenditures to build plants, is really huge. So if you can mitigate some of those costs to an existing facility, it really helps you a lot. Now, how big are chemicals nowadays? It's still growing quite rapidly. We are now around 330 million tons. Most of it is really made, most of it is really made from these 7, say, starting molecules. You can see they're all quite reduced. Only methanol is a little bit oxidized, and that is a major difference actually when we start from biomass. And if you compare that to the current bio-based chemicals and materials, then that is already substantial, 50 million tons, but certainly most of it is in the non-food starch and cellulose fibers and derivatives area. So if you look at biomass as a starting material, you have to keep some things in mind. First of all is that each process basically has its own requirement. If you look at the fermentation, or if you look at the catalytic conversion, or if you look at an hydrothermal conversion to certain molecules, you have different requirements. So when you think about, is this feedstock suitable for a certain process, you really need to know the requirement of that process. So keep that in mind. Another important thing is, for example, the purity of your glucose stream. So that asks for quite some refining for some aspects, while, for example, for the production of ethanol, you can start with a very diverse stream. What is also an important aspect in the whole thing is the downstream process of product and required purity of the product, and quite often aspects like crystallization, distillation, or membrane filtration are part of it. So in that respect, I think the bioeconomy and certainly a biorefinery is a truly interdisciplinary approach where really the intelligence of the different unit operations need to be combined to become cost competitive. Now, last but not least, on the longer term, there's a lot of discussion in the public arena now about food versus fuel. That is to some extent relevant, but on the other hand, it is our learning that, companies like Coke and Danone want to keep away from, say, food products like corn or maize or wheat, but on the other hand, they don't really willing to pay a lot more for that. So if you want to use forestry biomass for this kind of processes, you should have a point at your horizon where you are cost competitive, else it won't work. Now, an important part is in the whole thing is, do we see this as a pull or as a push? I think personally, if you're not able to create market pull, it will be a very difficult and rough trajectory. And market pull should come actually from the brand owners. And in our perspective, at the moment, for example, the chemical companies, they are not really pulling yet. I think still quite often we see actually in the field that it is still a technology push, or for example by the ag companies like or by government. So this are just a couple of examples of what the market thinks. Some of them are already a couple of years old, but it really shows that although the approaches are different of the different companies, that the global brand owners really want to go to reduction of their carbon footprint, or by recycling, or by replacing it by bio-based materials. And I think that is really a promising aspect, and it also really drives this industry, I think, at the moment. Now this is a little bit to give you some background on where are we now in the bio-based polymer production. So this is the situation by 2015. Now what you see actually, and that might surprise some of you, is that in the past polylactic acid was always the biggest, but the last couple of years it has been really replaced by biopolyethylene and bio-PET. And that bio-PET, only the ethylene glycol is replaced. So you see that market implementation goes much faster if you have a product that can be easily fed in current processing systems. Now you see also quite a few of the other ones. So total production is already significant and is expected to grow quite rapidly in the upcoming time. Now, I'm also involved in the IEA Bioenergy Task 42 on biorefineries, and we made a study basically what the status is now of the different molecules, who and which parties were producing them, and we made a table out of it. It are quite a lot of data, and I don't know if the presentation become available for the audience, but I will go through it very quickly. I only want to highlight a little bit that what we see here, if you look at the companies, I mean, if you look at the names, you can see that it's quite a global affair. You see quite a few of ag companies like Cargill involved. You see some chemical companies like Braskem, DuPont involved, Solvay. And you see also quite a few of SME companies involved. So it is a quite diverse field, and you can see some of the molecules are already in commercial production, while other ones are basically at a pilot scale. So there happens quite a bit. In principle, technically we can replace all the current chemicals by bio-based chemicals. The big challenge is really to do that cost competitive. And yeah, I made the remark earlier, but I like to stress it again. If you start, for example, for carbohydrates, we have a C6O6, so H12 molecule to start with. And so in a way that we have a lot of oxygen what we carry into the factory, and quite often the product is less oxidized, so you actually lose a lot of weight in the whole process. Well, if you start with a fossil resource, in general you oxidize the product over the processing and you add weight. So basically that is quite a disadvantage for biomass, what is quite often overlooked at first sight. So keep that in mind. Now this product, I won't go into much detail much more. I like to discuss now a little bit better, say, the drop-in versus novel functionality kind of aspects. Now, what do I mean with that? Now, a drop-in, then the molecule is exactly the same bio-based as petrochemical-based, while novel functionality, it means that the bio-based molecule, for example, this furan dicarboxylic acid, looks like terephthalic acid, but it has a different structure, so it gives you different kind of products. Now, what are now the advantages and disadvantages? Now, in general, arrows going up means better, arrows going down means worse, and this means more or less equal. So what you can see, market acceptance is for drop-ins much higher, because a unique molecule, you have to tell the story. Speed of introduction is higher. Fitting existing infrastructure is better. But on the other side, it has also a much higher oil and feedstock price sensitivity, because basically if oil prices go down and your biomass goes up, I mean, nothing keeps your customers from moving back to oil-based. Sustainability is in general, can be better, but I mean, it's variable. You don't create a unique market space. So that is a big disadvantage. Scalability is in general easier, and also legislation like REACH and so on is much easier. So the picture is quite diverse, and I think both choices have their merits. But as Avantium, we really choose for a unique molecule, and I will give you some aspects of why we are happy that we choose that one. 2 minutes, okay. Can I go faster? Now, the interesting part here is basically that you have improved barrier properties. A lot for oxygen, but also for water and for CO2. And that means that you can really change the whole packaging concept. And what does that mean? That instead of going just a replacement one-on-one PET, PEF, you can really replace, for example, aluminum cans or glass by PEF. What has a lot of advantages for example, weight or cost price, etc., etc. So, now, partly it was serendipity that we found that the barrier properties were better, but it really shows you that if you're going for unique molecules, you can find serendipity. If you go for the used ones, that chance, of course, much lower. Now, is this big? Now, this is just give you an idea that this is the current PET market, so it's around 65 million tons. Only bottles is already 2 million tons. And only Coke is already using 2 million tons of the 20 million tons. So that really means that if you have Coke on your side and they are willing to make that transition, then you can really create market pool, because else this is virtually impossible because of all kind of aspects. Like, for example, the safety applications. A new molecule, you have to go through REACH, you have to get FDA and EFSA approval for food contact. All those kind of aspects needs to be done. At the same time, you have to really prove that you can recycle the material, and what happens if you bring, for example, PEF in the PET stream, etc., etc. So if you don't really have companies like Coke and Danone saying, okay, we want that, and this is important, parties in the whole value chain are very difficult to motivate to put in effort to prove this. This is just an example of some of the current biorefineries which are in Europe at a demonstration or commercial scale. And yeah, conclusions, I think, yeah, we skip that one for the time constraint probably.
Thank you, Ed.
Yeah, welcome.
We will come back. We have now already had electronics on paper and then biorefinery concept. You will see that the future bioeconomy will be very diverse. And I guess that when Olli Ikkala is going to present next, so it will become even more diverse. So please, Olli.
Yes, I don't know whether in a good direction or bad direction. Anyway, I selected the title, What Can Biology Teach for Material Scientists and Technologists? So I suffer from being a physicist. I guess it's also Magnus' fate. And we have to learn other fields to be useful. He has learned so much biology and electronics. I'm trying to learn a little bit chemistry and perhaps also a little bit biology. So I'm from the Department of Applied Physics and heading the Center of Excellence Molecular Engineering of Biosynthetic Hybrid Materials Research. What a monster name. Anyway, tomorrow there's a lab tour. Those who would like to see, we have quite nice tools, for example, very good electron microscopes, so please join the tours. So basically I'm addressing the point that if people talk about renewable or sustainable materials, people think that they are in some sense lousy, bad, mechanically weak, expensive, and so on. Now, what people, when they do materials for engineering applications, nearly always people use mixtures because not a single material is suitable for its mechanical properties. And so the classic approach has been to make nanocomposites. So for example, take reinforcement, mix, for example, carbon fibers or nanofiber glass fibers to make skis, or mix flakes to make Toyota bumpers, or to make the airplane wings by mixing carbon nanofibers. We know that it has not been so easy, and this is a reason for example, why the new Airbus and the Boeing has been delayed for several years to go to the market. One of the points, and this is a little bit oversimplified, is that it's quite difficult to have the proper properties. It's usually easy to get strong but not tough materials, or not strong but tough materials. So I have some things to show you. Here's a scissor, so I demonstrate what means a brittle material. Each material has defects, and so I can make a defect to the material here. And now it's strained, the crack grows. It's not flow tolerant. And that's a little bit problem, for example, in the airplane wings, if the cracks start to propagate. And also, let's say, here is my dear Nokia phone. This is the other extreme. So if I drop it, it breaks because it has glasses. So that's not tough. Then, of course, I can have materials which are tough, that where the cracks don't propagate here, for example. But these are not very strong. And so this comes a kind of major problem for a material scientist to have all the whole trinity, toughness, strength, and everything in the same material. And so here is, for example, materials which are certainly deformable, but they are not strong. So how to solve this problem? So let's solve the problem. I have somewhere even more presents. This is a nice guy who has solved the problem. So this is a mollusk or abalone, and especially the ladies would really appreciate the shiny surface here. And this is the reason why it's used for jewels. But this is the downsides of this, because it's obviously a little bit expensive. Now, what is the structure for that? So this is there are nano-sized sheets of marble. You think marble is brittle, but it's nano-sized. It's glued together with a very clear and nice assembly. It's a self-assembly. They have been organized. And these consume energy in the way, if there's a crack, the crack deviates in the tortuous path. So one of the clues in the biological materials to have the whole trinity, stiff, strong, and tough, is to make self-assemblies, to have the reinforced units, and then construct energy dissipation in here. The other material which is similar is a little bit silk, where this is purely polymer. And there are reinforcing units, so-called beta sheets, crystalline domains, 3 nanometer in its diameter. And they are connected by segments of polymers which contain so-called sacrificial bonds, which consume energy in deformation. So, nature and these two materials have materials properties approaching those of metals. The silk has even properties which correspond to turbine steel. It's very, very good. Now comes the question, can we make these kinds of materials? So over several years we have been trying to do this, and we are slowly approaching. So this is a way how we presently do. We take inorganic sheets, coat them in polymers, and then let them self-assemble. And 3 years or 4 years ago, we had a material which had self-assembled inorganic sheets as glued by the polymer, and we call it pearl of nacre mimic generation 1. It has a strength higher than pearl of nacre, and the nacre was tough, but our material was not yet. But now these 3 guys, who is Maria Moritz, Johanna Sorvari, and Andre Krösel, they have been approaching to a method that has very high strength and it's tough. it may be even better than the real nacre. And we are trying to make it a product sooner or later. And there's even the first predicted application, what we think, but I'm not going to say it to you. Let's go now to a more general. Why to consider biological constants and materials? So I wanted to convince you that having a bio-based origin does not mean that it has to be a poor material, like the starch-based renewable plastic bags. If you buy beer from the shop, they don't last until home, then it's terrible. So if we could just make materials which mimic, let the nature do the invention, and you just mimic. And that's not even very easy, that I would say. So there are several possible sources: cellulose, nanocellulose, proteins. And then I give a claim, which can be right or not right. I think it is right. I think that biological production is slowly becoming cost-effective and bulk. I think qualitatively that is true. And then something which is a little bit arguable, but I think it's also true, that oil-based production is slowly becoming less cost-effective, because sooner or later the sources become rare. So there has to be some time, a break-even point. I don't know when it's in 15 years, 50 years, 100 years, or 1,000 years, but there has to be. And then it's good to prepare for that time. And then biological production allows more exactly controlled materials, like silk and the others. Now, and also there's another point. So the biological organisms have also some other functions, and sooner or later we would, based on Magnus, it means sooner, we are going to have materials which interface the biological and synthetic world. So here is the other example, and why I'm interested in cellulosics. Of course, cellulosics is interesting for me because it's very abundant, but it also has very good properties. So the crystalline part of the cellulose it's stiff, it's strong, like in the steel, and then it means that, let's say, one just have to be able to cleave the part of the woods in the crystalline form. And basically there are two forms available. One form is long and entangled, a few nanometer fibers. They are called nanofibrillated cellulose, and short rod-like materials, which are called nanocrystals. And then comes the question, because these have the properties of steel, how can we transfer it to exciting materials? And that's not so easy. So the first question, what we would like to answer is that if we have paper, classic paper, and here is paper, if I can do this is brittle. If we take nanocellulose, can we make something which is not brittle? And this has not been so much addressed before, because it's very, very difficult. And this just shows that basically it's possible to do tough nanocellulose films which are not brittle. He specifically wanted that I'm not talking about chemistry, so I'm not talking about chemistry. I can just say that we can construct so-called supramocha bonds here, which in the side chains of nanocellulose do the thing that in deformation they slide past each other. It's a little bit like in the silk. In fact, it's inspired by the silk, but a little different architecture. Now the chairman is very nervous already. Just a few things. So this is one of the what the nature also tells us: how to make dirt-repellent surfaces on some plant surfaces by surface patternings and chemical modification of waxes. I'm not going to show anything which are related to these kind of dirt-repellent surfaces, but I'm just going to say that if we try to mimic and learn how nature does the following thing, we can do something else. For example, materials which absorb very specifically oils or water. And they could be useful, for example, in environmental aspects. Also, they could be useful for carbon dioxide capture. And these kinds of things are progressing very many different places in the world right now. So, I'm coming to the end very soon. The biological production. So, I got this from Markus Linder, who is a genetic engineer specializing for material science. And so, this is a year, and this is a price which shows that the DNA production price goes down. And you see that it's a logarithm scale, it goes very deeply. And then comes, and this is a possibility for the future. So he was describing, Magnus was describing how electronics developed. And the development of electronics was based on modularity. You had transistors, diodes, and all kinds of the parts which you modularly assemble to the system. The same is happening in biology, and this is called synthetic biology. And this is going to change material science. And there's also a working culture difference happening, that there was so-called hacking. In the old days, there was building electronics and also making software. It was the hacking culture, in good and also in bad. And then there are three-dimensional printers. They make the hacking culture to make materials by printing different shapes. But the next generation of hacking is the synthetic biology hacking. And this is interesting that this opens the difficult field of genetic engineering also for undergraduate students, even for the school children. So I think this is a future to let the children to do the most innovative works because they are fresh. So here is a Helsinki team which was just in Boston in the competition of iGEM International Genetically Engineered Machines competition. It didn't win, but it got a special prize. And we would like to support so much of these very young people to find very new ideas of working. So the last transparency is just, I let it there, that there are very many different functionalities with biologically inspired materials, and it just takes that you have to think differently. There are lots of options. So that's it.
Thank you, Olli. So I think it's time to start the panel discussion. As I sent you some questions related to, you remember that our team today was about to discuss about from basic or scientific research to innovations, and at least based on the understanding what I got from your presentations, there are a lot of new research is ongoing. One thing what I'm like always have been thinking is that between industry and academia is the communication. So my first question relates to the thing that is it so that do we researchers understand what are the bottlenecks from industrial point of view, and do industrial collaborators understand what are the research targets performed at universities? So do we have a common understanding, or is that still some kind of challenge? Especially in we see here a lot of new things are coming, and is that something that is still causing problems? Magnus?
I can start. So the traditional way of looking at the innovations, or start with research and then hopefully it's innovation and then some kind of spin out or transfer to industry and so on. I think this linear flow of knowledge is very dangerous. I think we have to look at the converse situation, that industry should be present in academia to transfer fundamental challenges and needs, and in my experience is that many of the best ideas we have got in the group that we have been working with has actually been from fundamental challenges expressed by industry. So I think this twin direction of transfer of ideas and challenges are important. So I think this discussion that they're problematic to work together, I think it's because it's a unidirectional flow of knowledge, which I think that's the first thing you have to take away. There needs to be give and take from both sides, otherwise collaboration will never work.
Mm-hmm. I think that type of comments were also yesterday mentioned very, about this linear. It's very, very, very true. Ed, do you have any comments to this? I mean, do we understand what you are doing in a company? I mean, researchers.
I think there are a couple of big differences. I mean, first of all, I think that my presentation, although I didn't go in too much detail, really shows that it is really a multidisciplinary action. And I think sometimes universities have, or certainly university groups have to adjust that their area of expertise is not our critical bottleneck. And that is quite something what is sometimes missing. I think also what is missing is really that university doesn't really start into good discussions with industry. And I think maybe similar to what Magnus says, I mean, quite often really a discussion leads to a very much clearer problem definition and subsequently an approach to solve the problem. And sometimes we get the impression that university thinks to know what our problem is and then comes to us with the solution, while in reality that is not our problem. But if they start to approach us more open-minded, so to first starting to know more about the process and what we are doing and what we try to achieve, etc., I mean, it becomes much easier to also define then a real problem and a strategy to solve it.
So it means that the basic science, basic fundamental understanding is, of course, the strength of university, and we should bring that to your community.
Yeah, but also with not immediately with a solution-based approach, but an inquiry-based approach.
Mm-hmm. Olli?
I think one of the problems is to make the right question. And so I've been working 10 years in the industry, and so I have experience from both sides. And so it's too easy in the industry. If I was sitting in the side of the industry, it was too easy to say that, oh yes, those university guys, they don't have any understanding of the real life, and vice versa. So it requires long-standing creation of trust from both sides, I think. So that, let's say, ultimately one can ask the right question. For example, if the question in the production is that, let's say, it's just that, let's say, the efficiency of the production is not proper and the material properties are not proper, so it comes how to identify what is the real bottleneck on the production, and it may really require something which is very profound scientifically. And in those cases, I would say it would really make sense to make the collaboration, but it may take time to go so far. It's too easy not to stop kind of starting understanding before going to the ultimate questions.
Mm-hmm. So I'm like maybe the next topic I would like to raise is related to the biggest challenges. I mean, what are the biggest challenges in the bioeconomy area you see to? I mean, we have a lot of possibilities, as we can see, and there are a lot of changes happening. But how you see what are the biggest challenges? It can be from innovative or business ecosystem, innovation ecosystem point of view, or it can be, of course, I mean, you can answer the way you want, but I mean, how you see that? Where are the biggest challenges today? Who?
Yeah, I thought about it. basically three things. I mean, one is already, I think in the bioeconomy, capex is really an important. So capital expenditures is really a major hurdle to get new processes implemented, especially because, I mean, initial steps are quite often much more expensive than a final situation. So that relates to the second one. I mean, you really need brand owner commitment, and you need the total value chain what is able to absorb the extra cost. For example, I gave the example of Coca-Cola. Coca-Cola said that by 2020, all their ethylene glycol, what is basically one of the two building blocks of the polymer, will be bio-based. That will be at a higher cost, but they have in their models anticipated that on the longer term it can be cost competitive, and by doing so they will initiate production, competition, etc., and come there. If you don't have a company like Coca-Cola who is really pulling the wagon, it will be very difficult just to bring it as from a push side, a new molecule in the market. So getting that brand owner commitment, this is maybe one of the few positive examples. Most times, the marketing department might want to use it, but they are not quite willing to pay for it in general. So I think that are the biggest. Yeah, maybe the last one is what we see is that the chemical companies as a whole, so think about the BPs and the BASF, etc. They are quite slow in really making change. So they are not really, and they are typical, of course, business to business kind of companies. So they are not the ones who are initiating change.
Okay, yes, Magnus.
Also would like to add to these comments. One challenge is, of course, when we as scientists come to, for instance, the forest industry or paper or packaging industry, where they measure everything in metric tons, and we measure in the electronics world in functions. So if there are economists out there that could invent a good kick-out economy model for these new startups, where both the metric ton community and also the number of function can be summed up in a good business model. I think that is a tremendous challenge to bring new technology, where we typically, for the NFC, we would be happy to supply enormous amount of components with only 1 ton of NFC. That is a challenge.
Yeah, wet or dry?
NFC is never dry. That's what I have learned.
Yes.
It's always hygroscopic.
Because if it contains 99.5% of water, so it's a very good business if you sell it wet.
Yeah.
But 1 ton is 1 ton.
Olli, did you have anything about this? You had something, I guess.
Yeah, I was kind of thinking that if I see the question from the materials point of view, and I see what's happening in the world, I would like to say that there's lots of similar related work around. So I would even like to say that there's a little bit like overcrowding. Some of the ideas and areas are overcrowded, whereas some let's say, perhaps there should be some more totally fresh ideas coming out to find the real niches where the originality could be coming more better kind of to the real products. Then perhaps it's also that let's say when the finally there, especially if there will be a synthetic biology included, then one has to be very careful with the general opinions because one has to master so that let's say there are no erroneous kind of feelings or expectations in the media, And also, perhaps, what about this? If you think what has happened in the energy field just during the last year or two, the new gas findings and things like that, they have suddenly changed the situation in the politics. So I think there's also are there also possibilities for a little bit short-sighted politics to just to get postpone a little bit the bioeconomy because now it's one can have an easy life for next coming a few years. I don't know.
Yeah, those are of course very good points and quite complicated ones. I have one question before we take question from audience, and that relates a little bit that we talk about here about influence or impact of research and also I would say education to our innovation system in bioeconomy. And one area that in Aalto University, of course, we have put a lot of emphasis to entrepreneurship and startup actions. But if I look at the bioeconomy area, it's proportionally, we do not have at the moment here so many startups, so many SME companies at the moment. And how you think about that? What's the reason for that type of indication? Of course, we do our best to increase that. That is my duty as a dean of our school and as I think that for our society we have to have those. But how you think about these reasons why, Magnus, you are working in a way in the area of mixed ICT and bioeconomy. So can we get some boost from that way, or I mean, how you see these reasons why we do not have so many SMEs or startups in this area?
Maybe it's in reflecting the tradition in the bio industry in the past, where there have been a few large companies running the business, paper production and so on. But I don't think it's solely the university responsibilities to generate these environments where companies are started. I think this should spread out much more in the society. I'm not in favor that universities always should have this responsibility to create this environment and facilitate spin-outs. I think that should be a common responsibility in society, both industry, society and university. And we have incubators, startup incubators. I'm not sure that they are the best solution. These kind of institutions are the best solutions for entrepreneurship. I'm a little bit hesitant to those.
It's good to hear. Maybe we had debate already in a previous session, but we can discuss that later. Ed, what do you think about? About the reasoning.
A couple of things I think which are important. One is that it is not really. Most times it's not a one idea invention, but it is really a combination of several things. So. That makes it more difficult, I think, just, for example, from within a university to really bring it quickly to the market. The other thing is that it is really a capital-intensive process to scale it up and to bring it to the market. And I think that both in, say, biotechnology and now also in the bioeconomy, there have been already too many failures. I think compared to ICT, venture capitalists are relatively, let's say, conservative in financing this area, and that hampers it. And I think that also has to do probably also with government. Both in Europe but also in other places in the world, there have been very mixed signals in, for example, subsidies or legislation around biofuels or other things, what really makes it very tricky to invest in a plant, and then later on, the rules are changed and then suddenly you can't earn any money anymore. And all those kind of things together makes it at the moment rather difficult to really raise a lot of money to scale this up and to do, or further develop it and scale it up.
Okay, okay, Olli.
Yeah, so might it be that, let's say, the chemical industry and forest industry has classically been kind of big industry, and so perhaps there start to be some kind of paradigm changes also in this respect. I just emphasize that, let's say, for example, in the field of polymer industry, which is dominated by the big ones, but let's say there are also very successful, very small companies. I think Magnus knows much more than me, but for example, just thinking those companies which make electronic nose material, so they just make a few grams per year, but they make as much turnover as a big low-grade chemical industry. So it just, I've been kind of, let's say, asking to identify the fresh new ideas, and perhaps there could be possibilities for not stepping on the toes of the big companies, but let's say if there's a totally new fresh idea, then perhaps there are more room for small enterprises.
Yeah, but then you're not making a bioeconomy.
Yes, so it's just a small part.
No, but I mean, for those kind of applications, only functionality is leading. And if your biomolecule has a higher functionality, then you're a winner. But I mean, for those kind of applications, it doesn't really matter if it is fossil-based or if it is biomass-based, then it is really the functionality what's leading.
Yeah, you are in the sense right, but let's say if the building blocks still are based from the biological materials, and so I think that, let's say, if the when one gets some of the applications in the market, then it's a kind of flagship, and it may have the small snowball effect that then it's easier to have the next applications in the market. I realize that it's not a question of hundreds of thousands of tons, at least immediately. But I think it's a kind of paradigm that these days, if one immediately wants to have this huge production, then it can be a so big barrier to do anything.
And it is not that we want that, but you have to face reality. Just to give you an example, yes, in China now there are oxidation plants built for paraxylene to PTA, purified terephthalic acid, of 2 million tons. And we want to build a factory of 50,000 kilotons. And so that is a factor, a lot. I mean, it is impossible to do that at the same cost level. And the same cost level is quite quickly, that's already maybe twice as expensive, yes, and those differences in scale. If you are going to the market and say, okay, I have a polymer that is twice as expensive for a bottle, then it doesn't work. But if you are going, I mean, we could use our polymers for way other kind of things, and then it's much higher added value. But then you have the problem that you don't sell out your 50 kiloton plant, because 50 kiloton seems maybe not so much, but it is still, I mean, if you look at a bottle, what, depending on the size, weighs 20 grams, you can still make quite a few bottles out of 50 kiloton. So it is easily said, but you are really squeezed in how to make, you're trying to cross a river, but the amount of stepping stones you have are very minimal and they are very wide apart. So you really have to make a very directed jump to come up a stepping stone, and then hopefully you keep your balance and keep standing there.
Yes. So that's absolutely true when there's a kind of bulk application where you try to go. So there can be some smaller scale applications where there are not so many applications yet, and you.
Okay, but in that respect, I mean, you agree with me that if you are going for drop-in molecules, because drop-in molecules you immediately are competed with the petrochemical counterpart, and then you don't have this playing field. So then you have to go to unique applications.
I agree.
Oh, okay.
I
Yeah,
would like
Magnus.
to add one thing. So I have been following various kind of directions in electronics. Recently I looked into printed circuit boards. Those are the flexible boards that are everywhere in computers and cell phones and so on. And that market is around $50 billion. It's a pretty big market. The tough regulations that are set up by governments actually force the industry to go into use paper and aluminum as the conductor because that's recyclable. So don't underestimate what politicians actually can kick both industry, existing industry, and scientists in it. So I would, what we are seeking for are brave politicians that actually can force the society to become. That's what we are needing, and it happens to printed circuit board, and it's amazing to see. Mühlbauer, all the big industries making printed circuit boards, they are moving slowly but slowly into paper. So all of a sudden they might come to your company and look for coatings that are biomaterials because this is the profile or the brand name owners can not only drag the entire industry into a bio-society. We need politicians and brave politicians.
That's an excellent comment, I
So
have
where
to
are
say.
they?
So any questions from audience? The light is coming again. The sun, I don't blame sun, it's sunny, but
Thanks. I enjoy very much the discussion and the presentation. You mentioned relation and collaboration between industry and the university. Let's see, if you look at the university, research is driven by curiosity. Industry, research is driven by money. If you discuss what we are producing at the university, we are producing PhD. That means many cases is not related to project, is related to bringing to our student their diploma. And industry has to produce products. Both of us publish at least some information. University publish in journal, industry publish on patent, and we are able, each of us, to read the paper of the other. So we can be aware of that. And then we can each one go and see how we can collaborate. The second aspect is university produce researchers and industry uses them. So you are very well in industry, you are very well aware of that, and you can choose what you want. Even also industry can choose any collaboration that is usual. So it is a system which finally works if the people want to collaborate or to see each other what's going on. So I don't think we have to make a canvas for this collaboration. This collaboration can be easily fitted by the way we are in the same world and we know each other what we are doing. Of course, some don't know, but that is to blame, that's all. Now, concerning the chemical, I have heard maybe that you want to mimic nature to make them stronger, but I think something else is important in nature. Nature has the ability to repair, and that is the most important part. Of course, solidity or something wrong, and I think that there is also some of this research done.
Yes, of course, this is done very much. Materials which repair and have higher functions. The situation seems to be that right now that, let's say, there are not very many of those applications where they could be extremely suitable at the moment. I know that there was, for example, a French company who tried to develop something to the self-healing materials to the car applications, but then there were some problems with the chemicals, oil and gasoline, and the lifetime in their with their materials. So it's not so easy.
I have been a jury member of a PhD of Professor Laine, which is Nobel Prize in Strasbourg, and the student present his PhD and then cut a piece of plastic, put one of the other, press, and it was repaired.
So that's very standard procedure these days.
But it has to be maybe more explored,
Yeah.
even if it is more difficult.
Yes, so one of the pictures which I showed also makes the same. So the one which requires to make tough cellulose-based materials, that requires the same kind of ability to reform the bonds, because then the material is in the way under deformation. It can exchange interactions. So this is a really one of the breakthrough inventions in that field was Professor Ludwig Leibler from Paris, who showed these kinds of things, and it kind of launched huge work around the world for self-healing materials.
Can I add one thing?
Yeah, sure.
Your remark versus industry versus academia. In our case, yes, I mean, so we make a polymer what has a higher resistance for oxygen transport. For us, as a company, basically only the result is important, yes? But at the same time, we really like to know what is the reason behind it. And that is something where we can collaborate very well with universities to get the fundamental knowledge of why it works the way it works, and then to see if we can use that knowledge again to change our product for other properties, etc. So I think quite often, if there are good possibilities for collaboration, and yeah.
In this regard, to Olli, in your biomaterial based on cellulose, do you have to take into consideration, or do you worry about possible enzymatic attack of the 1,4 bond by fungi or enzymes?
Yes, of course, they had to be taken into account. Yes, absolutely. In some application, it's very desirable. For example, in the biological application, that let's say they would be biodegradable, which is not usually the situation in the cellulose. So it's important to engineer the biodegradability. In some cases, in the constructional application, so it's very harmful to have the degradation, and then but there are ways to attack this.
Something that Jean-Marie Laine doesn't have to worry about his polymers.
Yes, correct.
Okay, any other questions? Then I will have a last question from my side, and could you describe or guess what is going to happen from your own perspective before 2030? I mean, your field. Where is these things you have shown today, where they are to be, where they are going? Just a vision. Guess. Yes.
I think our area about electroactive polymers, I agree fully with Olli. It will move more and more into plant science, and I think maybe around 2030 or maybe 2040, I think you will actually be able to put the seed into the ground and grow electronics. I think that's already happening now, and about 2030 you will be able to grow a computing system from the ground. That's the vision.
And it requires some science, some educational things, and some industrial collaboration, I guess.
Yeah, and you need to bring electronics people, the computer science, and you need to bring plant biologists and all the gene modifiers and synthetic people together. And that's where I see the future will go, very much with electronic functionality.
One could even think that, let's say, because just we have been playing with the same kind of crazy idea, is that, let's say, perhaps one could even have new kinds of heat pumps when it's growing inside of the earth. And
yes, absolutely.
You are not lacking in ideas or visions. That is excellent vision, I have to say. Ed, what do you think in your field?
I think it was raised already before, but I think the most important part is really that we need to have a kind of global consensus where we want to move the Earth to. And if that is really to a circular economy, I think then there are many opportunities. If we really lead by, say, economic constraints, I'm really afraid that we will continue on the current route, basically until we are running into collapse in a very steep transition period. And I hope that we have wise enough leaders to prevent that. But yeah, we are not always confirmed by that.
Okay, thank you. I think it's time to give a big hand to all the panelists and speakers.